One. But nobody. Oh, okay. Okay, it's technical. So can I put here or somewhere here?
No. Okay, good. Thank you for coming. Today we have Professor Prodan Bulka from Institute of Molecular Physics from Poznan, Poland, and he will tell us something about copper pair splitter in photonic cavity.
Thank you. Thank you for invitation personally to Michael. But I'm very glad to be here because I have here old friends. We participated in the European project, and many times we met together with Mikhail, with David and Rosa, so we know each other. And I'm even second time here on this nice island, and I'll be talking about these things. The lecture is devoted to detection Andreev scatterings or on some copper pair splitter by the photonic cavity. And here's this plan of the lecture. First, a very broad introduction. How one can use these cavities to study electronic properties in nanostructure. It will be very general. Next, I go into more details, how one can see a response of this cavity on when you put nanostructure. Here's one example of such thing. It'd be third point when I show you how I calculate, because I'm theorist, but how it is connected with a real system, such research. And of course, the main part is connected to the Cooper per splitter. Here's some symbols. You have superconducting reservoir with Cooper pairs, and they are injected into two quantum dots. And can they split? And they, of course, they are entangled between them. And of course, one can measure currents there, whether you have good entanglement or not so good. And of course, at the end, some remarks. And let me start with quantum computer technology. You heard for sure a lot about superconductors, quantum computing. And there are many companies interested, for example, Google, IBM, Intel, D-Wave, and so on. And but there are different approaches to this, to solve this. Main problem is how to build a chip with many qubits operating coherently. And of course, it's a main problem. Still, it is in some stage in the halfway, because they produce already some computers, but quantum computer, but still the number of chips and number of qubits is too small for commercial. And there are 4 different approaches based on superconductors. Here it is one example from IBM, and I mentioned here that Google, IBM, Intel, Rigetti, D-Wave, and smaller companies as well. The other method, but less popular, and the chip is not so, has no so many qubits. It's on rapid ion processor. And here's one example from quantum science. There are different companies: Alpine, Atom Computing, Ion, Quantinuum, this from Quantinuum, and Squirrel Laser. There are also proposal used photonics. There are some company, I think from USA, and 2 from China. There are also proposal on semiconductor spin qubits, but they obtain the chips with only 4 qubits, so it's not so much. This is several hundred. So my idea was, can we use this technology, because they're quite well developed technology, to our purposes? We are interested in this nanostructure. Can we use this technology as a byproduct of this development to study what we studied in the past, but it was not available by this technique in the past? So, few words about cavity quantum electrodynamics, how it works, how one can apply it, and how one theorist can calculate some quantities which can be addressed to the experiment. And here's some examples. I use this paper by Cotte. She was very nice, but it was the first paper I show you also have it. And here you see that's really cavity. You have mirror, metallic mirror, but we use this superconducting. But it is not important. And you put inside some crystal with defects, and you can find dynamics of this defect, electronic structure of this defect. You can, it is some interaction of photons. In this pink color is shown how the photons can interact with the system. The more advanced it is this superconducting device. You have here some superconducting grain. There is some Josephson junction. Of course, it is a scheme only. And you have some control, but here you have these photonic fields which could interact with the grain and disturb the cavity. So, and here it is another example. And you see here was one electrode, second electrode, and it is some quantum dot made by graphene. You see, it's some graphene sheet there. And of course, you can control this quantum dot by the gate. There is another gate. You can apply it even AC field there. And you can, once again, measure response of this cavity. It is example one, but you can find in more modern work by Clerk and others that it is various already examples to use this cavity to detect nature of electronic nature in the system. For us, interesting it is quantum dots. Here you have quantum dots. You see many electrons. There is small thing here. You see the size of such system is quite large. 1 millimeter for me is very large. But this one is in the scale of nanometers. The other example is diamond crystal containing spin in. You see some crystal on the chip connected to this device, what I wanted to talk about. And here is another example. Here it is a ferromagnetic sphere of yttrium iron garnet, this black one. And you see it is some cavity. Honestly speaking, it is made of copper. So it is not superconducting, but the physics is the same. You produce some waves, photons in that, and they interact with this yttrium iron garnet, and you excite spin waves in such a system. There are many others, as for example, nano electromechanical oscillator, separate acoustic resonator, so you can study also phonons and Ball acoustic resonator. But I'm interested mostly in this part. And you can find that there's a lot of physical problems you can study by this technique. Here, for example, you have two quantum dots, one built on such a system. You have one quantum dot, second quantum dot, and you see there is another one put into the cavity. Here it is shown amplitude of electric field. So you can excite it by electric field and study this spin entanglement. Here's another example that you can study the transition from the singlet state or to quantum dots. You have singlet and triplet, and you can study that. You can study Majorana fermions. You can study by this technique some quantum wells in such a system, multi-layer system. You can study Kondo physics. There's a subject interested by Rosa. You can study photonics. You see that there are some gaps and there are some vibration. And once again, there's good review, Nature Review Physics, so very good journals. You can find details. Okay, so it was general introduction, but now let's go to some details to show you that I can calculate something and how to calculate it, what is the physics behind, and be devoted to how to construct circuits and how we connect our mesosystem to this cavity. And first, what we need to produce a chip. And of course, you know that technology prefers planar chip, not such one. And you see here, it is shown how electric, magnetic and electric field is in this coaxial cable. But when you cut it, you obtain such structure, and the electric field is so, and magnetic is around this conductor. Yeah, so you have planar, but it's important for technology and so on. And here is the scheme for some older paper, how we can use this electric field for study some nanoscopic or mesoscopic system. Here you have some boxes, maybe some quantum dots there. And when the amplitude is very large, you have very large response to that system. And you can study. Of course, you can study also this trepid atoms. You should put it in the maximum of this electric field. Of course, you can change the configuration and use this magnetic component to study some magnetic excitation or magnetic dynamics. Is it okay? And here is the same, that when you have crystal with magnetic impurities, you can use this magnetic field around the wire. So it is technology. And now the principle of how to construct such circuit. Here it is typical LC resonator. You teach students for sure that you can generate microwaves of waves when you have C and capacitor and inductor here. And of course, you can describe it. You can use the first Kirchhoff rule, which is the change in time of Q. It is charge, and it is related with the flux. And of course, you can define L is the definition of the inductance. Of course, you use the second Kirchhoff law given here. And what is important that you obtain some resonance frequency, the frequency of producing waves. Electronic waves, in principle, it is in microwave regime. And other important quantity is this characteristic impedance defined by this one. And of course, we are interested in superconducting device. So we want to use Josephson junction resonator. It is in principle very similar because, as you know, that Josephson junction has some nonlinear impedance defined here, nonlinear on the flux included here. And of course, you want to construct network of such things. Here is how it is used in literature, that such device with capacitor and this nonlinear inductor, it is denoted in this form. Sorry?
The phi in the left part is the voltage of the flux.
Phi, it is.
This is voltage. Voltage drop. Right.
It could be voltage, but it could be also flux.
Flux is in the right. The cosine, this is a flux.
Sorry?
In the cosine function, this is a flux.
This is a, yes, I'll show you later because you can put here some external magnetic field, but you can write here even with a magnetic field.
Five is not.
I think it's voltage, right?
Five is not.
It is not, and to the not you can apply the voltage, or can you change the flux? I saw you in a minute that the quantities are conjugate, because it is classical approach to this resonator, but we want to have quantum resonator. And when you apply it, first you should write some Lagrange and so on, next to transform to Hamiltonian, and now you have operators, Q operator and phi operator, and conjugated. So this phi there, it was either Q or phi. And of course, when you have such this linear harmonic oscillator, so you can express it by bosonic operators, A and B, the creation and annihilation of photons. And you can express these quantities. So you have, in principle, this harmonic oscillator description. For LC, of course, you have a little bit more complex when you have superconducting device with a Josephson junction. And of course, how to couple this device to our meso system. Here it is, this my system can consider, which will be considered, but you see here, one can do it with coupling capacitively, by capacitor. So you will change charge. And of course, you produce some waves here. But, so this is a resonator. Important thing that you have also, you can also analyze the system. You can see, it is in principle, one can say this cavity. And you can also analyze, you can see in experiment, measure in experiment, the reflection coefficient. The reflection coefficient has imaginary and real part. Yes, the experiments can do it, but you can change this by some probing voltage. There is another method you can, you see, by inductive coupling, because we want to have an answer, the communication between our system, which we want to investigate, and how it is seen in this cavity. Of course, it is, the name is maybe misleading, but you can think about such things. And here it is the background about response for such a system. And it is based on input-output theory. It's a popular book about quantum optics. You can find this input-output theory in many textbooks. And what is the main subject to do it? You can measure input or output, or input and output for a transmission. Yeah. But if you introduce inside our nanosystem, you do disturb the cavity. And this, we want to measure this disruption. And here it is how you can calculate this reflection coefficient or transmission coefficient in this input-output theory. The important thing is resonance frequency, but you can also apply this prop frequency, what I mentioned. They do such things in experiment. Of course, there are also descriptions about dissipation, internal dissipation of the cavity and external dissipation of cavity. And what is new, this response for the system, it depends when you are coupled capacitively or inductively, it be response given here. Of course, very similar as here, but and the key quantity, what we are interested in, is this one. Of course, this depends on this probing frequency, but not known in principle are this coupling constant, G1, and to some internal degree of freedom or connection to the network. It is not known. It is known only from experiment. So it is the problem to obtain a large enough coupling to see the signal, some perturbation. So how to do the physicists? They use linear response or Kubo formula. You have Hamiltonian, not term, and some perturbation which depends on time. It could be this, our wave, oscillating waves. And here it is how we describe it. It is some operator B of this term. This is very general. It can apply to any system. And here it is small coupling because we want to have only perturbation. And here it is how in this Kubo formula is obtained. You obtain average because you measure some average, but it is not perturbed. And here it is response function. And of course, we are interested in this, what is in between. And what is this one? When you have operator, this one and that one, so you, for this system, you have such correlation. These are quantum correlations used, because you see this some commutator. And of course, but this zero means that it is when the coupling is absent, because it was derived in this response theory. Okay, so we are prepared. And as I mentioned, we have two approaches. We have capacitive coupling, and in this capacitive coupling, you have variation of voltage on the capacitor. Yes? There are some variation with time, this AC variation, and it disturbs the local charge operator. And in such situation, we are interested in local charge susceptibility. Of course, it is time dependent, so we can make Fourier transform and we can calculate it. And it is seen in this experiment. Or when you have inductive coupling, we change this phi, or what you mentioned. You can change the flux with time. Of course, it is small perturbation. Still, we are in this linear regime. And here we obtain such quantity. Once again, this quantum one, and you have current correlation measure. Okay, so let's go now to some examples. Let me take once again. It is we put some system with two quantum dots. It is one quantum dot, second quantum dot, and it is they're connected to some electrodes, normal electrodes. It is here, and you can even change the voltage on one electron and see how it is transport. Can be detected by photons applied to the system. Important here would be that we can control the relative position of the quantum levels in this quantum dot system. We can shift the level applying the gate voltage not shown here. And I would like to test my approach and follow some previous papers, how it works. And it is from the paper by Ballrap group from ETH Zurich. It's very good laboratory. And you see here this resonator I shown already. And you see there are many. This is Joseph John Junction, so it's connected. There are connected several squids. Why? Because we want to have a strong coupling, this device to charge oscillation observed in the system. And of course, once again, we have this analyzer. You have analyzed in and out. You can also change to probe this frequency. And here it is a schema and how this looks really for some system. You have here quantum dots, one quantum dot, second quantum dot. There are some electrodes to control all these things, to shift these levels. I mentioned that we can shift relative position of the level. And once again, when you increase, here it is nanometers, and effectively you have millimeters. They construct some such thing. And what they measure? They measure, for experiment, I mentioned that we can measure reflectance. For example, you can measure also transmission, but it is detailed. And what they do, they have some resonant frequency is here. They could also change this resonant, but as well, they can change this probing frequency. So they can use such a map. And where is our system, this nano one? The nano system is described by this dashed line, which says you, of course, for such a system, you have two levels. And these two levels are more or less described by, described by the difference between the tuning of this relative position of the level on the quantum dot. So it is a map with respect to the tuning. You can manipulate by gate voltages applied to the dots, and you can obtain such a map. It is, of course, modulus. You can go deeper because, as I mentioned, this quantity is complex. So you can extract complex value and real value and to see. And real value is connected with the shift of the resonance frequency. Delta mi is this shift of the cavity, frequency cavity, when we introduce this our system with two quantum dots. And you see what would be if we change the resonance frequency. Here it is small frequency. You see all is in gigahertz range. So what we investigate, the dynamics in gigahertz range. So you have one and you can increase. And all is probed by this probing frequency. So, and I put here what could be calculated by green function theory. With some simplifications that temperature is 0 and so on, and all it is in equilibrium. So we have no electronic transfer. And you see that I can find that the shape, this blue one, is more or less similar to that. But of course, one can also measure the shift of the damping. I put here that how it looks from theoretical point of view. And you see, this one corresponds more or less to this one, when I change the parameters and change also the frequency. And here the same. You see, very similar shape. Of course, the main problem is it, my calculation, this coupling constant, good enough, so large enough for such a system. Okay, what I done, I performed calculation at equilibrium. It's more or less what was observed in the experiment. You see that there's deviation of this. Once again, this dotted line presents the qubit, how it changes with some parameter when I have this detuning. And when it meets with resonance frequency, it is, of course, interaction, photons and with electron, and you have such thing. Interesting here, when you looked, I have here reflection coefficient. But when you look on numbers, in my case, the reflection coefficient can be larger than 1. You say it should be between 1 and 0 and not bigger. But it was also confirmed experimentally. You have here amplification. The nanosystem can amplify the signal in this cavity of this electronic device attached. Here, it is for equilibrium, but I can calculate the system also for non-equilibrium. For any applied voltage to the electrodes. And of course, you can see some electronic transport. And the limit of large U, large it means that we have the voltage larger that takes both levels in. You can calculate it analytically. But what you see here, the shape is completely different. And you can say, okay, here this absorption and emission are different. Okay, you can go into details. I present you results for this because it's quite clear how to. In general, you should calculate this integral, which is in this response function numerically, but here you can write such simple things. And next, what I did, it is spectral decomposition. Because here we have polarization excitation. In this business, you call each denominator. You see, this one is still different. We call it as a relaxator. And how they relaxate, so we can describe dynamics of such a system. And this one is for intra-level or relaxation process, but you have also term related with emission and absorption. So you can see, and once again, that how it changed with the voltage. For 0, it was its equilibrium, it's non-large V, and here is some between. Okay. But it was the test, my test, because I want to go to this Cooper per splitter and to see entanglement and this the dynamics of the system. And once again, this resonator I described already, this analyzer, which also changed the probing frequency, this resonator with a good coupling to the system. It's a very strong coupling. And here we have reservoir of Cooper pairs. And we want to study, we have 2 quantum dots, and the system is capacitively coupled to the one of the dot. And I want to study entanglement between electrons, which could be on such a system when the dots are close to superconductor. We have proximity effect, and they have some Cooper pairs, for example, such one as presented here. And of course, you can measure processes, how this Cooper pair is transferred to the left or right electrode. And you see, I show you that when we are talking about Andreev reflection, because in the moment I show you that we consider holes and electrons going in this direction or opposite direction. Okay, so the problem was already, this Cooper pair splitter was already studied 10 years ago by my colleagues from Poznan, Jan Martinek, with collaboration with Schoneberger and Baumgartner from Switzerland, as I remember. And they produced very nice paper, experimental and theoretical one, showing how this entanglement can be seen in such a splitter. It is, you see some roller coaster with some particles or pairs. You see one pair has spin up, the other one has spin down, and they were interested about these entanglement processes. They were interested whether the Bell relation for entanglement, this quantumness of the system were related. But I came back to this, but I am interested in dynamics of such processes and dissipation in such a system. Can we see or study by this cavity? And in this cavity, you have Andreev reflection. Andreev scattering is with so-called retroreflection. What is a retroreflection? When an electron is tunneled here through the quantum dots to the superconductor, they produce Cooper pair, but it should be kept number of particles. The hole is ejected from this. And it is simply that hole is electron is injected and hole is ejected. This is Andreev reflection. So I want to study such a processes, describe it, and study by this technique which I present for double dots. And of course, it's some mathematics, but it's shortly I should write the Hamiltonian. It is this term describes electrodes. It is this two normal, one superconducting. Quantum dots, we have two quantum dots, and the coupling between the reservoir and this quantum dot system. Of course, I use some notation and I use some approximation, for example, to see physics. I use the gap, the superconducting is very large, so I can neglect some processes because I'm interested only in this Cooper pair transfer, not excitation or odd state, how Rosa presented. And I assume also that I consider only such states. It is, as you remember, it is superconducting state with some electron at the dot one, and the second one is singlet state. I assume that is not zero. Of course, I neglect triplet and intradot pairing and so on, so on, so on. So after such some simplification, I obtain Andreev qubit. I will have Andreev qubit, and in principle, I will start study this dynamics of this Andreev qubits under applied voltage to that where we have splitter. And once again, here's written this Andreev qubit on the quantum dot. Of course, you put after that some information about electrons. And once again, that when you have such a qubit, you have two states with plus and minus, and it's combination of when you have no electron on both dot, or you have this interdot singlet. And of course, you can derive that you have two states, and it is the separation between these qubit states. Important is different from the case considered for double quantum dot, that here the main quantity is the average position of electrons on the dot. This one, that one. This would be break electron-hole symmetry. Of course, when you consider real Andreev qubit, you should add some odd stage, but for qubit built on such an Andreev states, these odd states produce leakage, so it will destroy you the qubit states. So they are not interested. Okay, and now I perform the calculation. One important and for theories is that I calculate some total green function with electrons and so on. And of course, one can see that it's a product of two processes presented here. You see that one process is when the hole from the right electrode goes to this transport, so goes to this quantum dot number 2, and at the same time you have jump of electron from this quantum dot system entanglement to this one. But it is the same equivalent process opposite. Hole jumps here and electron jumps something. Of course, this is for the system without magnetic field or without spin orbit interaction, which breaks such nice things. But here I want to present only for this case. And formally, it is not easy to write this separate, and I can calculate many things. For example, I can calculate it currents by using Landau-Boutique formula with transmission, and you see the transmission has two peaks. One, it is connected with transition to lower state of qubit, and it is lower, higher state qubit, and so on. And it is given here. But I'm not interested in current because I cannot measure it in my device with cavity. I'm interested in this case because I have coupling, local charge. I have this capacitive coupling, so I inject some polarization on this quantum dot system. And for my, have some green function and some complicated, but it's difficult to present when you want to say about it. But once again, in this limit large voltage and temperature equals 0, you have once again very similar but a little bit different what I have obtained for two quantum dots. I perform once again this spectral decomposition to show dynamics of relaxator. And you see here one term connected with absorption, and term connected with emission. Of course, it is mathematical, and I have this function put into this input-output formula and see what happens to what happens to cavity? Okay, but when I put it once again, I presented here the modulus of reflectance, and when you have such a system, when it is in equilibrium, so of course you have Cooper pair jumping on them, coming back because it is in equilibrium. But you can, and once again, you see something that is red one showing that even you have amplification, as I mentioned, is above the unit. So we have such a case. Of course, once again, you have this qubit situation. With respect now, I detune the position of both, dots. So it is with respect. And this picture is for when we have delta equals zero. So we have electron hole symmetry. I show you in a moment what would be when you go. And of course, you see there is changes with voltage. And of course, once again, you can investigate frequency shift, what would happen in the system, about broadening dynamics, dissipation in the system, and so on for different voltages. And you see there are, I understand all these details, how it's changed, how the Andreev level comes into these studies. And of course, one break the electron hole symmetry, this is some parameter, and you see how it is changed. I understand why it is plateau here, what is happening here. It is so that when you have such situation, this window transport is not allowed in this region. But when you have some moderate voltage, you see even here you have some structure there. Okay, so I'm going to the end because I want to summarize and to say whether it's possible to measure, because I would like to address it to experimentate. Then, so my goal has been to show charge dynamics in this Cooper pair splitter. Yeah, or Andreev qubit, special kind of Andreev qubit, studied by means of this microwaves. But these theories have been can be related to some experiment. And the most important is the system proximates quite good. And here I use that it's such value of this approximation, because this approximation makes you the separation of Andreev states. And in an experiment on carbon nanotube quantum dots, it is this value. There's a single quantum dots and so on, so on. I gave here reference. And the other one is important to have a good large coupling, because when the coupling is small, the resonance is weak, and we cannot see this details of this frequency shift and so on. And I use here this value, but in experiment I present here was Carino and others, where they use such, once again, device. They had stronger even. Of course, I should honestly say that my Cooper pair splitter is simplified. I forgot, I neglected electron-electron transfers or intra-dot Cooper pairs change, which should be taken into account. So thank you for your attention.
Thank you very much for very nice talk. Some questions?
The reflection coefficient can tell if the singular state is coherent or not. For example, you can have a coherent superposition of up, down, down, up, but you can have a classical mixture of up, down, and down, up, right?
Once again. No.
The measurement of the reflection coefficient
Yeah.
can tell the difference between two cases, that in one case you have a coherent superposition of up, down, and down, up, the singular state, or just classical mixture of up, down, and down.
No, because in this system, I have not this magnetic field with spin orbital interactions. One cannot differentiate. That's the same. Simply I calculated for one and the same result you obtain for the sigma. There are not correlation between this process, I can say. Here. Okay, this is the answer. Because there are independent channels, or one process and the other one. It's completely separated. As in paramagnetic case, you have electrons with spin up and down. And transport for spin up is the same as transport for spin down. These currents are not correlated. Of course, when you introduce some interaction, so you breaks such a system, yes? But it's the same, that you have the degeneracy simply and you have no.
Thank you for the talk. I mean, especially these charge susceptibility calculations are hard to do. So
Sorry?
the charge susceptibility calculations are hard to do. When you have this big integral and then you are able to.
No. You see, I show you that it is so small matrix. It's 4 or 6.
Well, but still, I know a little bit about that.
I forgot about Coulomb interaction, but keep in mind that I have this singlet state. So for this case, I can make the VIX rule to split this to calculate this charge.
But my question was related because you consider that the case that intra-dot Coulomb interaction is infinite, which is okay because the dot's small, and so Coulomb repulsion is very. But also in this Andreev splitter, the two quantum dots, they are close to each other. So you also have interdot Coulomb interaction. So how about this interdot?
I've seen it breaks the picture a little bit.
Okay.
Of course, you can ask also what would be if I have a Coulomb interaction on the dot.
This is.
But in the window,
but between
they are higher in energy.
Okay.
We've seen even in calculation when we try to do it. But the physics is so complex that no interesting from physical point of view.
But in the experiment, you certainly you have this.
I've seen some paper, maybe they put inter dot hoping.
Well, but that's different. Interdot tunneling is different. What I mean is the interdot Coulomb interaction because it can give rise to, I don't know, like drag effects, Coulomb drag effects or something like this.
But in my experience, this makes nothing new in physics when you introduce you have Coulomb interaction in this physics because you have electrons, so they shift only the level.
In mean field, yes, but beyond mean field, I think there could be some correlations. But okay.
Okay.
So, thank you.
More questions? I have one question. Can you comment shortly on this regime when the reflection coefficient is larger than 1? This means that the system emits something.
Yeah, the system.
Who emits and why emits?
Sorry?
Who emits and why emits?
who emits and why. The system becomes amplifier.
Yeah.
And it is
Yeah, how it
known,
works.
and even it was confirmed experimentally that the system is an amplifier. Sure, you can construct some amplifier. In more details, I cannot
Okay,
say,
thank you.
but
Fine, thank you.
Yes.
People electrons which jump from into quantum two. Then they jump to normal level. During vision, they jump, they emit and why?
But this is the presence of
It's okay.
due to this, I mean, I don't know, but due to this.
But the emission means that you take energy from your system.
yeah.
Some
So I think this is the reflection of
the cavity.
yes,
This means that we emit from
this is
overlay splitter into cavity. We emit.
but this is a base.
But if you take energy from cavity.
So from this quantum dot,
Yeah.
from this electronic device, what you put into the cavity. Yeah.
This was my question. Okay.
Thank you.
Yeah, there's some pumping there.
This is unusual situation when the reflection coefficient is larger than 1. This means that square by modulus of transmission coefficient, this quantity which should be definitely positive, they are negative. Understand? Okay.
More questions? Then let's thank again.
Thank you.
The name of this person, right?